Hi. So we now come to the last lecture of this module number 7, where we have been discussing about query performance enhancing techniques, and bitmap indexes is one of them. So in this lecture we are going to talk about compression of bitmap indexes. So I'll tell you a little bit about data compression in general, and then I'll move on to run length encoding, which is the main encoding scheme used in bitmap indexes, and there are certain variants and its variants, and then there are two very popular compression schemes called as byte aligned bitmap codes and world aligned hybrid. But for a first course, it is not required to go into these advanced techniques, which are quite intricate. But what I'll do is I'll give you a lot of details about run length encoding, and these two schemes are actually derived from run length encoding. So let me talk on compression of data. So data compression basically implies that you are trying to send or store a smaller number of bits than there are originally in the data. And although there are many methods that have been proposed in the literature so far, so based on those methods, you can classify data compression methods into two categories. One is lossless and the other is lossy. And lossless basically when you are trying to work with text or compressed text or programs which are again texts. So you use lossless because you cannot afford to have any kind of losses or any kind of errors to not errors but any kind of loss to occur, right? So run length encoding, Huffman, and Lempel-Ziv, LZ. So these three are the main techniques here, although we'll be focusing only on the run length here, right? But if you do any course on data compression, so you will be looking at Huffman and Lempel-Ziv, LZ compression techniques. And on the other hand, we have lossy methods, like you have the concept, so here we can afford to have some kind of losses, and the popular techniques are like JPEG, which we are using for images, MPEG also for moving for videos, and MP3 for sound. And there are new versions that have come up, right? So if you now see, there is something called as MP4, and there is something called as MPEG-4 also, and similarly for other techniques for images as well. So basically here, since we are dealing here with mainly the multimedia data, so if you are doing any course on multimedia data, so these kind of compression techniques you would learn in such a course. So just for the sake of completeness, this thing has been put here. So run length encoding, so let us focus on that. So is probably the simplest method of compression, and it can be used to compress data made of any combination of symbols. So basically it talks about data represented as symbols, right? So if you have heard of this genome sequence, so it is ACTG, and if you look at binary sequence, so it is zeros and ones, or any number of any combination of any kind of symbols, right? So you can apply run length encoding on that. So general idea behind this method is to replace consecutive repeating occurrences of a symbol by one occurrence of the symbol followed by its by the number of occurrences, or followed by its length, or the length of the what we call as the run. So next few slides will give you a clear idea of this. So suppose this is my data. So there are 4 symbols in this, A, B, N and M. So you can see B appears 9 times, A appears 16 times, N appears 1 time, and M appears 10 times. So the compressed data would look like this. So that's how I can save on the space by doing this, using this kind of representation. And you can see that one run, so this is one run of B's, right? So, and it is terminated by the occurrence of the other symbol. So that's how we typically identify a run. So the longer the runs, the more would be the compression. And now here is a sequence of zeros and ones, which we are typically interested in bitmaps. Bitmaps are nothing but sequence and zeros and ones. So what we have done here is that we are focusing on the runs of zeros, and that's how we have done. So 14 zeros in the beginning right here, so 14 is represented as binary here. Then there is 4, so again that is, and likewise we have done it in and this is, like you can see, 12, right, 4 and 8, and this is 0, right? So okay, so this is how we do it. So you can see here that the original bit string, which is in the box, white box above, is represented by a compressed string, which is given in the yellow box below this. Now let me give you some technical aspects of this. So suppose there is an attribute f, cardinality m, of table cardinality n, right? So table cardinality n means the number of records are n. So this is the number of records. So n is the number of records, and cardinality means number of distinct values in the column. So number of bits required to represent the bitmap on F will be m into n. So suppose there are two distinct values, say male and female, and there are 100 records, so there will be 100 bits, right? And similarly for female there will be 100 bits, so total bits would be 200. So 200 is nothing but 100 2, that is the cardinality, into 100, that is 200. So 200 bits. So if block size is 4096 bytes, that is 4 kilobytes, then we can fit around 32,768 bits in one block, right? And total number of blocks required for any bit sequence would be then given by mn by 32768. And this number increases with an increase in m. So as the number of distinct values increase, the number of ones get decreased, right? So what happens is the probability of getting a 1 depends on the cardinality of the column on which, or the attribute on which it is created. So if ones are rare, then the set of all bit vectors becomes sparse, becomes a sparse bit matrix or sparse matrix, and we can encode bit vectors so that they take much fewer than n bits on an average. So you can see here, so if there is this male and I have to represent them by, say, so suppose there are 20 rows, so there will be 20 bits, so this would be 20 bits. So what, and 20 is nothing but n in this case. So what I'm saying is, if there are fewer ones, like in this case, I can represent it by much less than n bits on an average. Okay, so that is what is the idea. And a common encoding for this is run length encoding. So now I'm going to give you the details of run length encoding. So represent a run. So let me clear this. So represent a run, that is a sequence of I zeros followed by a 1 by some suitable binary encoding of the integer I. So what you have is, suppose you have 1 2 3 4 5, and then it is terminated by the appearance of the other symbol. So what you see here is the run is of length 5, so I is 5, right? So I don't, in run length encoding, I don't simply write 0 5, right? So, or the length directly. So what we do is we represent this 5 by a suitable binary representation, right? And this you do for all the, so suppose there is another one here, so this length is here, I is equal to 1. So like this, if suppose this is my bit sequence totally, so then whatever I write for this part 0001, say 1 2 3 4 5 ones, so whatever is its run length encoded version, plus I'll write the encoded version of 01, and then I concatenate these two strings, right? And this is done for all bit vectors in a bitmap. So finally the whole matrix gets compressed using this concept. So now let me give you some examples. So consider the bit vector 0001 and 01. So it contains two runs, as you can see. One is, sorry, there should be another 0 here. It's a typo. So it contains two runs, 0001 and 01, of lengths 3 and 1 respectively. So 3 is equal to 1 1 in binary, and 1 is equal to 1 in binary, right? So the run length encoding, if I just use the binary representation of I, so if I just use the binary representation of I, so let us see what happens. So this would become, these two ones correspond to this green, and let me change the color so that you understand clearly, red, and this 01 is represented by 1. So in all 6 characters or 6 bits are represented by 3 bits. So 50% compression I am doing. So the bit vector, now if I look at another bit vector, say 01 and 001. Now this 01 is represented by the first one, and again I need to change the color, and this bit green part is represented by these two. Now for both these bit strings that I considered, 0001, 01 and 01 and 0001, both have the same encoding, right, when I use the binary representation of the length for run length encoding. So if I give you 111, now you can decode it in two ways. One is 01 and the other is 1. So this is wrong. So any encoding scheme should allow or should lead to a unique decoding, right? So here I can decode it into two ways depending upon whether I take these two together or these two together, right? So this scheme cannot be used. So as a result, we cannot use binary representation of lengths for run length encoding. So now the question is, what do we do? So what we do in this case is, I'll clear this. So let j is equal to the number of bits in the binary representation of I. So suppose I is equal to, say, 3. Okay, so how many bits I need? I need 2 bits. Okay, so j is 2. So if I is equal to 3, j is equal to 2. Okay, so j is approximately equal to, so as you can see, j is approximately equal to log 2 I. Right. And what we do is we take this j, and then whatever j is, suppose j comes out to be 4. So I write it as j minus 1 is equal to 3 ones. So I write it as 1 1 1 and a single 0. So j minus 1 ones and a single 0. And then what we do is we follow this with I in binary. So what was I? 3, right? So it will be 0 1 1 in binary. So that's what we do. So so consider this example where there are 13 zeros. I is equal to 13. So I is equal to 13. So that means j is equal to 4. Okay. So this would begin with so j minus 1. Okay, sorry, j here in this case was j is equal to 2. So j minus 1 was 1. So this would have become, sorry, I'm taking this example first. So if j minus 1 is equal to 1, so 1 0, and then I in binary is 1 1. Okay, so this would be the for this case. Now if I is equal to 13, j is equal to 14, or j is equal to 4, so that means I would have 3 ones followed by a 0, and then 13 in binary. 13 in binary is 1101. So this would be the run length encoded version of the bit string given here. So I hope you have understood this is a very simple scheme. So basically I look at the length, I then look at the number of bits I would need to represent the length. So then I represent that length using a unary number system. Right here I am using ones as the unary number system. Then I follow it up with a 0, and then I write the length, that is I, in binary. So this is what I do. So encode so 001 0001 01, so 2 runs of 3 and 1. For I, this is the same example I took earlier, where I used simply the binary representation of I. So I is equal to 3, therefore j is equal to 2. So this would be encoded as, so if j is equal to 2, so I write j minus 1 once, that means 1 1 followed by a 0, and then followed by this in binary. Now similarly for the other run 0 1, so what I do here, so I is equal to 1, so therefore j is also equal to 1. So therefore j minus 1 0 once, that means 0 once, so it will start with a 0 and followed by 1 in binary, that is 1. So the binary encode, the run length encoding of the given bit vector would be 101101. So now I am saying, how do I go back and decode? So there are 2 steps in any encoding scheme or any compression scheme, and that is compression and decompression, and encoding and decoding. So we typically call run length encoding. So we talk about encoding and decoding. Encoding part we have just seen. So now let us look at the decoding part. So what we need to look at here is that we take the encoded scheme or the encoded sequence, and we look at the occurrence of the first 0. So first 0 occurs at the second position. Therefore this 0 represents what? It represents j, the value of j. It gives you the value of j. So what happens is that we had represented j minus 1 once and followed it with a 0. So if I count the if I look at the position of 0, it will give me the value of j. So here j, so j is equal to 2, and I know that if j is equal to 2, the next 2 bits would represent the length of the run in binary. So next 2 bits are 1 1. So like you can see here, so the first 4 bits are decoded as, so it tells me that 1 1 means the length is 3. So 3 is the length, so that means 3 zeros followed by 1. So that is how I decode the first part. Now I look at the second part, and again look, so the first bit is 0 in this case, right? So the first bit is 0, so therefore j is equal to 1. So 0 is at position 1, so j is equal to 1. So next bit is 1, so the last 2 bits are decoded as 0 1. So it's a sequence of it's a run of length 1. So that is how it is represented. So I get this as the decoder. So when you do decode it like this, so you'll note that we'll always have a 1 in the last bit. So trailing zeros cannot be recovered, and if you are particular about recovering the zeros, so that you can recover from the cardinality of the table. So if you know, say suppose this was for a sequence which was for a table where there were 12 attributes or 12 records, so you will append as many zeros as you want. But the question is, do we need to recover trailing zeros? So the answer is that no, we don't need the trailing zeros, because zeros don't contribute to either of the operations that we carry out, that is or not, or and. So we don't need to talk about. So it is by default assumed that all the remaining bits are filled with 0 on the right hand side. So now I'll take some examples to illustrate this whole concept. So this example you already saw when I talked about bitmaps. So here you have the age bitmaps and the salary bitmaps, right? So two bitmap indexes, one on age and the other on salary. So and or operations. So decode. So the easiest way out is that you decode and operate on the original bit vectors. So whatever run length encoded bit sequences are given to you, so you decode them and apply the and or operations like you do in normal circumstances, right? However, we do not need to decode the entire bit vector at once. So that is how this run length encoding is useful. So what we do is we decode one run at a time, right? And when we carry out the OR operation, so produce a 1 whenever we encounter a 1 in either bit vector, and produce a 1 if and only if both operands have the next one at the same position. So that's how we do, but this operation is slightly more complicated, like if you want to apply and or OR operations on the encoded bit vectors, right? So let us see how it is done. So age 25 and age 30, so these are the two bit vectors. So corresponding encoded bit vectors are 00 110 111 and 110 111 respectively. And by now I think you are in a position to see that these are the correct encoded versions of run length encoded versions of the given bit vectors. So I'm not going to show it again, so let us assume that these are correct. So decode, okay, sorry, I pressed. So what I need to do is I need to do an OR between age 25. So my query is retrieve all the customers whose age is either 25 or 30. So you can see here, so I have encoded them in the form of run length encoding, right? So these are the two in the brackets are the run length encoded versions of the bit strings. So what we do is, so I'm giving you the algorithm to do that. So first runs of both bit vectors are easily decoded as 0 and 7, because this starts with a 1, right? Okay. So its length is 0, the first run, and the second case 1 2 3 4 5 6 7, so length is 7. So this we can see, and that you can see from the encoded vector also. So the first 0 is at 1, position 1, so j is equal to 1. Okay, so when j is equal to 1, that means what? There are how many zeros? So there are 0 zeros, so it starts with a 1. So respective implying that the first bit vector has first 1 at position 1 and second bit vector has first 1 at position 8. So we generate 1, so I'm doing an OR, so I generate a 1 in position 1 and the next one is at position 9, because there are 7 zeros in between, so this and this. Okay, so therefore the bit vector generated by OR operation is followed by 6 zeros followed by 1 sorry, okay, followed by 1 at the 8th, sorry, this is not, there are 7 zeros, so 8th position coming from age 30, followed by 1 coming from age 25 at position 9. Okay, so this results, so this tells me that there will be a 1 at the first position, there will be a 1, so this is coming from age 25 and this 9th is also coming from age 25, and I'll just use another color to, and this one is coming from age 30. Okay, so this is the result set. So you could see that I did not decode the entire vectors completely to do the OR operation. So the first 8th and 9th records are retrieved. So on the same lines you can, so if I change this operation to say AND, right, so I want you to try this on your own. So this works in similar manner. Only thing is that you have to output 1 only when there is 1 in both the bit vectors. And operation efficient compression bitmaps compression methods. So there are two, basically BBC, that is byte aligned bitmap code, so which was proposed by Antoshenkov, and so you can look at this paper in 94, and there were some improvements. This was proposed in 1996. Similarly, there is another one, so word aligned. So it is Wu et al. And given in 2004, and then again an improvement in 2006. And you can see the important part here is that both of them use the run length encoding. And the main difference between these two is that, as the name suggests, so one is byte aligned and the other is word aligned, which is like 32 bits, and this is 8 bits. So this is the major difference. And they are adopted in real systems. So you can see any version of Oracle after 7.3 uses BBC, and this word aligned WA is used in this Lawrence Berkeley lab for high energy physics related experiments. So so you can see these two encoded schemes based on the run length encoding. But in this course, we are not going to talk in detail about these two methods. But if you have understood the run length encoding, so these are pretty straightforward. And this is a kind of a result. So you can see on the x-axis is space, right? On the y-axis is speed, right? So if you look at WA, that is, WA is supposed to be better, right? So you can see that it is giving you better speed than BBC, and it is also saving you space, although it takes more space than BBC, but speed is important, right? So it gives you a good combination of both speed and space, right? So I'll now wind up this particular module. So in this module you looked at 4 basic techniques. So one is aggregation, other is partitioning, then view metallization, and bitmap indexes. So bitmap indexes was the last one that we just finished. So you can see that there is aggregation, and here the main concepts are that of sparsity failure. So it is about pre-computing aggregates, and there is a middleware aggregate navigator that is used. And then we come to partitioning, where you partition the data, and mostly with respect to time, because it has its definition remains the same over time. It does not change. And moreover, partitioning with respect to time gives you many other advantages in terms of administration and maintenance of the data in the data warehouse. Then we come to view metallization, which is nothing but pre-computing the results and storing them. So this helps us in speeding up the queries. And it is important to note that aggregations are also implemented as metallized views, and other operation that is typically so all kinds of aggregations, all kinds of joins, and the combinations of joins and aggregates are typically supported in most relational systems, right? Although the concept of view metallization theoretically applies to any kind of pre-computation. And then we recently discussed bitmap indexes, which is a very efficient way to retrieve data, large amounts of data from the data warehouse, and it is also multidimensional in nature, so it naturally fits multidimensional queries. So with that, I wind up this module on performance enhancement techniques in a data warehousing environment, and the next module is going to be on metadata. Thank you.